All right, everybody. So what we're going to do today is we're going to talk a little bit about some of these exponent properties. So it doesn't really matter what order I talk about them in, but what I'm going to do is I'm going to show you the, generalized, it doesn't really matter what power it is, notation, and I'm also going to show it to you with like concrete powers and numbers. But again, whenever you're doing these, this result right here is always the fastest way to do it. And what I'm gonna do that seems more complicated than it has to be is I'm going to show you why it works. So let's use this with some concrete powers. And what I mean by concrete is defined powers, like a number or something like that, a concrete example versus abstract. So usually we see it something like x squared times x cubed or something like that. This is just saying some base and a matching base. That's why they're using a, or you might see it with different letters. These are saying it doesn't really matter what power it is. They could be the same, they could be different. In this case, it doesn't really matter. But as a reminder about what an exponent means, before we go into that, let's just say that we have some base and any power, okay? So it could be like 3. That's saying that we have 3 factors of that base. They're all being multiplied, so there's 3 of them. A lot of times students use the terminology, I'm just going to multiply b by itself that many times, and that, kind of gets a little confusing when you say I'm going to multiply b by itself 3 times, but then that kind of, students write weird stuff when they say it like that. But that's all the power means. It's just fast multiplication. So what I'm going to do here is I'm going to go ahead and kind of color code it a little bit and expand it. So this right here is x times x, because that's the definition of the exponent. And this right here is x times x times x. And then this multiplication symbol can be brought down. Because students often ask me, how do we know to multiply right there? Well, that was always there. We just kind of expanded x squared, we expanded x cubed, and stuff like that. But then if I go through and I look at this, it seems like I have 5 x's that are being multiplied, so my final answer is x to the 5th. Now, in actual practice, all you ever really have to do when you are multiplying 2 things with the same base is just add the exponents. 2 plus 3 is 5, so it ends up saving us a lot of time. Because what if this was a 20, and this is a 30, 20 plus 30 is 50. We don't want to have to write them all out every single time. Now, over here, we're going to do it the same way. We're going to use a concrete example. So let's just say that I have x to the 3 raised to the 4th power. And again, this will extend to if we have much higher exponents, if we do it the fast way. So this power right here is saying that's how many of the thing directly to the left of it. This entire thing is grouped up together and is being raised to the 4th power. So that's saying I have 4 factors of this being multiplied together, because that's what the exponent means. It doesn't matter what is being raised to the exponent. That's how many factors of that thing that you have. So in this case, if I were to write it all out, I'd have x cubed times x cubed times x cubed times x cubed. Notice I have 1, 2, 3, 4 factors of x cubed. And each one of these individually is x times x times x, bringing down this multiplication symbol. Same thing here, x times x times x. Bring down the multiplication symbol, x times x times x. Write down the multiplication symbol, and then x times x times x. And if I look at this, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 x's being multiplied, which is the definition of x to the 12th. So again, if these are much larger numbers, x to the 30th to the 4th power, you don't want to write out 4 factors of x to the 30th and then expand each one of them and count them all up and then get to x to the 120 or anything like that. You don't want to have to do that. So the fast way to do this one is just when you raise a power to another power, when you raise a base to a power and you raise that to another power, you just multiply your exponents. All right, well, let's look at this one on the top left. So we have 2 factors raised to a power. And the assertion is that you effectively, and I'm going to put quotes around this because you're not really distributing. You're effectively distributing that power onto both of them. I need to get you to watch out, though. If this is multiplication or division, like this one right here will also do the same thing, it works. This does not work if there's a plus sign in between or a minus sign. It only works if they under multiplication or division because they're effectively the same operation with caveats. Put a little asterisk somewhere in there for what I said right there. So let's use a concrete example. X squared times y to the 4th. And I'm going to raise that. I'm going to use a 3 here. And the reason I'm going to use a 3 here is not because it doesn't work with 4. It's less writing for me. And I'm going to raise it to the 2nd power, just to not have to extend all the way out here. Because the more factors I have to write, the longer it's going to be. So again, this is saying that's how many factors of this whole thing that I have. Let's make it a little bit harder on myself. So let's do x squared times y cubed all to the 3rd power. Notice I didn't have any powers right here, but this would be the same thing. A to the, doesn't really matter, m power, b to the o power. It doesn't really matter, not o, p. Then I'd raise them to that power. It'd be m, and then it would be p. I just didn't write these having powers themselves. But I'm going to do it this way, and then I'm going to do it without, a power. So it just has a power of 1. I just want to make sure that you understand it works for all caveats, and the properties can mix and match. So in this case right here, I'm just going to go ahead and expand this. I have x squared times y cubed. I'm going to put a multiplication symbol there, even though we don't have to write it when it's sitting like that. So that's 1 factor of that stuff times x squared times y cubed. That's the 2nd factor times x to the 2nd y cubed. So notice I have 1, 2, 3 factors of that thing, which is what the exponent means. All right, well, I'm going to expand each one of these individually. So this x squared becomes x times x. This y cubed becomes y times y times y. Same thing with this x squared. Same thing with that y cubed. Same thing with this x squared. And that y cubed. Now remember, multiplication is commutative, which means that you can change the order of it. So I can write all my x's next to each other if you want. 2, 3, 4, 5, 6. And again, everything in here that we've been doing is multiplication. And then I have 1, 2, 3 y's. Another 3 y's. I'm only underlining them to make sure I don't double count any of them. And then another set of y's. Still all being multiplied. And if I go ahead and count, I get 1, 2, 3, 4, 5, 6, x to the 6th. That's the definition of it, because I have 6 x's being multiplied. And right here I have 1, 2, 3, 4, 5, 6, 7, 8, 9 y's being multiplied. That's the definition of y to the 9th. But again, all I really had to do, especially if these are larger numbers, is effectively, but not really, distribute this power onto both of these, and then do my other exponent property where I raise a power to a power. Now, doing it a slightly different way, if I were to use the property where I effectively distribute this onto both of those and not expand them, each one of these things would be a power to a power. So if I want to use the other property instead of expanding each one of them, I can do that. And then x squared to the 3rd power, I raised a power to a power, so I multiplied the powers. Same thing over here for the y. 3 times 3 is 9. So, if you want to see it without any powers, effectively having a power of 1, could be this many things for all we know. If I raised all of those factors to the 2nd power, I'd have w, x, y, z, w, x, y, z. Now you have 2 factors of that stuff. I can change the order. W, w, x, x, y, y, z, z. W times w is w squared. Same thing with the x's, same thing with the y's, same thing with the z's. And notice all I effectively was doing was effectively distributing, but not actually distribution. We don't like calling it distribution, really. Now this one is the exact same power, because as you remember, I said multiplication and division are effectively the same operation. You're multiplying by the inverse. Division just has the caveat that you can't divide by 0. But multiplication and division are effectively the same operation, so it's going to work the exact same way. So why am I even doing it? Who knows? So a concrete example of just using a 2, this would be x over y times x over y, because that is 2 factors of that same thing being multiplied together. That's what that exponent means. So remember, when you multiply fractions, you multiply the top times the top and the bottom times the bottom, and that's what your answer is. So multiplying fractions is the easiest thing you can do with fractions. Just remember that you multiply the top times top over bottom times bottom, the numerator times the numerator over the denominator times the denominator. So I get x times x, which is the definition of x squared, and y times y in the bottom, which is the definition of y squared. If we want to use a different example, then we could say x squared over y cubed to the 2nd power, same idea. And then that's saying I have 2 factors of that same thing, x squared over y cubed times x squared over y cubed. And from here, I could do top times top and realize I'm multiplying 2 things with the same base. So I just add their powers, and I get x to the 4th. Or I can expand it. I'm going to do it both ways. I'm going to do it with the exponent property. And then on the bottom, I have y cubed times y cubed. Add the powers as y to the 6th. I'm going to get the same answer regardless. But maybe I don't want to do it like that. Maybe instead, I want to write out what it is. So for my x's, I have x times x x times x. Then I have y times y times y over y times y times y. And remember, when you're multiplying fractions, you multiply the top times the top over the bottom times the bottom. So x times x times x times x is x to the fourth. And y times y times y times y times y times y is y to the sixth. It's going to give you the same answer regardless. All right. Now, a to the 0. So anything to the 0, effectively anything to the 0 is defined to be 1. Now, this might not seem intuitive, but the first thing I'm going to do is I'm just going to show you. This is using it as a definition. It doesn't matter what it is. In calculus, there are a couple of caveats, but we're not going to talk too much about that. But the reason for it is when I said that x cubed was equal to x times x times x, that's true. But there's always this little invisible 1 there. You can multiply by an infinite amount of 1s, but in this case right here, this is what we're used to. But there's always this little invisible 1 that you can multiply by, because multiplying by 1 doesn't do anything. Notice if I were to do it like this, let me show you. Let's do x cubed. If I think of it like that, there's 3 factors of x times 1. And then x squared is 2 factors of x times 1. Notice multiplying by 1 doesn't do anything, and the rest of it stays the same as we're used to. So x to the 1, which we also just write as x, is going to be 1 factor of x. That's why it's just x. So x to the 0 has to be 1 times no x's. When I think of it like that, it makes more sense in my brain. Now, this over here, I can use this idea for my fractional powers right here. I wrote that wrong. That's not what I meant to do. You got to ignore that part. I was going to talk about radicals, and then I didn't. So basically, the idea here, as I fix my rushed error, a negative power basically says throw that base to that power into the denominator and make the power positive. That's what it really means. It just means that if it's in the numerator, you throw it into the denominator and you make the power positive. A concrete example of this would be x to the negative 2 is equal to 1 over x to the 2. It could also be something like 1 over x to the negative 3 is equal to x cubed. It's basically saying to get rid of that negative right there, throw it in the other side of the fraction. And it's still being multiplied. Now, students have a hard time with this one. 2x to the negative 2 would be equal to, that 2 isn't affected by the exponent, so it's going to stay in the numerator. Now, if you really want to show yourself this, you have 2 over 1. That's what this is. 2 is just 2 over 1. And it's being multiplied by x to the negative 2. So that's 1 over x squared using the property. And then, so that's 2 over x squared. If you don't want to go through that little bit of a step, if you want to do it more quickly, you can realize that this is going to get thrown in the denominator. And the denominator doesn't have anything in it, so it only has a 1 in it. And so it's still going to be multiplied onto that because that's the only operation happening between these two. So it becomes 2 over x cubed squared. But that's not the part that messes students up. The part that messes students up is if I were to have something like that. Again, it says move it into the numerator and make the power positive. So you could just jump straight into 2 times x squared is what that equals. Remember, multiplication is, there's no addition or subtraction here. Or you can write it out and say that if you remember how fractions work. Now, this is going to seem complicated for those of you that don't remember how to do fractions, and that's okay, because we're going to have a whole section on fractions to make sure that we understand, just in case we're still confused. So again, this is 2 over 1 is that 2 in the numerator. And using the exponent property for x to the negative 2, I have, instead of x to the negative 2, I have 1 over x to the 2. It's using my property. And remember, if you're dividing a fraction by a fraction, you flip the denominator and you multiply instead. Because those dividing by ones don't do anything. So it's the exact same idea. You get the exact same thing. There's a lot of ways to do it. You're going to find that that happens a lot in math. But let's use this idea. So we have this stuff. So I'm going to take this, and I'm going to expand it to include negative exponents. So remember, I had x cubed was 1 times 3 factors of x. X squared was 1 times 2 factors of x. X to the 1 was 1 times 1 factor of x. X to the 0 was 1 times no factors of x. So you have to think to yourself, well, how do we do this with negative ones? Well, x to the negative 1, you've got to remember that the opposite of multiplication is division. So if we're having a negative 1 in our power, that means that we're going to be dividing by that base instead. So that is going to be 1 times the inverse once of x. So the inverse of x once. That's what this is saying. That's what that negative 1 power is saying. It says, hey, it's 1 times the inverse of that base. So the multiplicative inverse is just the reciprocal. That's all it is. That's all it is. I'm going to have a whole video on additive inverses and multiplicative inverses. So x to the negative 2 is 1 times the multiplicative inverse of x twice. Now, maybe you don't want to think of it that way. Maybe you want to think of it a little bit differently. Instead of just saying, oh, it's got to be the inverse. Let's try x to the negative 1. Now, that negative 1 power is called the reciprocal power. So it just means take the reciprocal of whatever the base is. But we could also think of it as, hey, divide by that power instead this time. So you have 1 divided by x, because you're dividing by 1 factor of x. I like thinking of it as the multiplying by the inverse that many times, but it just depends on how it sits in your brain. And I will end up making another video on combining like terms as well. And I feel like if you're having confusions, I feel like the biggest confusions you will likely have will come from this one. I feel like another misconception you'll have is students have a big habit of taking this and kind of swapping the operations. This one right here, students have a huge habit of thinking that this applies, and this goes for my friend that was in Calculus 2 that gave me his notes. What he did was he saw this, and I put a big does not equals. He did like that, and he said that that was a squared plus b squared. Notice this plus sign in the middle. That does not work. And when we talk about binomial distribution and things like that, it'll make more sense. It does not equal that, even though students want to do that, because the reason is That's 2 factors of that thing. And notice a lot of students try to just do the first times the second, but what were to happen if I were to just distribute this onto both of those and then distribute again? So we'll talk about distribution in a future video, and I'm going to use this as an example. I'm going to throw out a little aside for those that are curious right now. If I were to take this and distribute it onto each one of those terms, multiply it onto each part, I would get A plus B times A plus, because it's this is going to distribute onto that A, plus what you get when this distributes on that. A plus B times B. Notice I still have parentheses, and I kind of don't want them, so I'm going to distribute this onto that and that. When it distributes onto A times A, you'll get A squared. When it distributes on the B, you'll get AB or BA. They're both the same thing. Multiplication is commutative. And I'm going to distribute this again, and I'll get AB. I like writing it like that. You don't have to. You can write it as BA. B times B is B squared. A squared plus, I have one AB plus another AB is 2AB. And I get that. Notice that is not equal to A squared plus B squared. And again, that is motivation for you to watch my combining like terms video and my future distribution video. Thank you.